All right, so good morning, everyone, and I want to thank you, the organizers, for an invitation to be here. Thank you. I think the reason why we were asked, Ohio State was asked really to participate in this meeting and in this session, originally it was a question about smart cities or smart communities, and you may know that Columbus has received a federal grant. We won the national grant for Become Even Smarter. So for the past 2 years, this City of Columbus and Ohio State and a number of industrial partners actually have been working on technology deployment to make Columbus one of the, I wouldn't say flagship smart cities because there's more in the United States, but we are those who are federally funded. And actually, we were supposed to provide lessons learned and reports to all the communities who would like to introduce technologies which would make cities smart. Now, it's a huge, giant topic, and of course, I can talk for hours about it, but we don't have hours, so I have decided today to speak about a work which is related to really my background. For a number of years at the university, I have been working mostly for the Department of Defense and the civilian side of the government related to global positioning systems, sensor integration for so-called assured navigation, which means navigation anytime, anywhere, with anything and any platform. So the recent work, the most recent work of my research team has been really focused on image-based navigation as related to autonomous vehicles. So essentially, I would like to walk you through what it takes to provide accurate position or localization for autonomous, automated and autonomous vehicles, how we do it, what are the accuracy requirements, and I will try to touch upon a little bit of the testing of those vehicles, as well as of the challenges, because somebody mentioned earlier today, essentially the standards for the autonomy really don't exist yet. They are being developed, but there is no consistent set how to test and what metrics we're supposed to meet for the autonomous vehicles. So just a brief definition, which you can find just about anywhere, of what is the smart city. So smart city is the one which is connected and uses multiple technologies to essentially improve the way the city operates, reduce the cost, preserve the environment, and make people's life easier. And if you look at all the smart components, just essentially anything, and everybody is supposed to be very smart in such a city. And by definition, if you have 5 of those technologies implemented in your city, you're already smart. To the best of my understanding, there is really no fully smart city in the world yet, but by 2025, we expect 26 of them to be fully operational as smart cities, most of them in Europe and in the United States. So of course, what comes with smart city, one of the components is smart mobility. And again, number of topics, as you can see right now, listed on this slide, really defined what the smart mobility is. Again, a giant topic. What I would like to focus today are those items in italics, essentially connected vehicles and cooperative navigation component, which also connects to the infrastructure which the smart city is supposed to provide for smart mobility. And the second component is really automated and autonomous vehicles. People mentioned today the electric vehicles, share rides, and many other components, which does create a system of smart mobility. I just want to mention, and the whole goal of introducing smart mobility is so-called 3 zeros, which really means low or no emissions, or very low carbon footprint. We are looking for low or no congestions, and again, it has to do with what we discussed. I think it was touched upon in the first talk this morning. Shared rides, possibly system which provides mobility to the user rather than the same number of vehicles that we have right now, and everybody owns a vehicle. And of course, no accident and fatalities, or very, very small number of those. So let me move on to a little bit more of the definitions I just had, because if we look at transportation, it's really not only the ground transportation, albeit I'll be focusing on ground transportation. I just want to emphasize that there is more in a smart city, right? If you look at the 3-dimensional map of a city, And all the mobility components, you have a traffic and you have pedestrian on the ground. You may have unmanned aerial systems in mid-air. You may have aircraft, and of course there is a navigation and communication system of satellites. And if you look at those, they are really forming layers of information and potentially then can provide navigation information to the layer below. So you can think of this as a layered sensing or layered communication. And all of this forms system of systems once, of course, everything is based on communications. So communications are really crucial. That's really one of the things you would need to see in smart cities. Again, I'm not going to go through the details because it was discussed in the first talk. We are pretty much, I agree with the comment earlier, we are somewhere between 2 and 3. I think depending on the company and the system we are discussing, the decision would be we are somewhere between 2 and number 3. So as you can see, as we progress towards 5, there is much less involvement from the driver. The vehicle essentially not only senses the environment, makes all the decisions, and drives by itself. So there is a distinction between automated and autonomous vehicles. So essentially, automated is what we have right now, when a lot of functions can be performed by the vehicle, but the driver is the one who takes, the final shots and decides, if the vehicle starts beeping saying, hey, I can't do anything, you take over the control, we can still do it. If you go to number 5, there's really no interaction with the driver, so you are really a passenger. A couple of things I want to mention. And again, this is just professional bias. I need to cover this. The high definition or geospatial data is just one component where we need. So far, those of you who have, and I think everybody does have a navigation component in your vehicle or on your smartphone, if you look at the resolution of the map and the type of the map that you have is nothing that you really can use for autonomous or automated navigation. It has to be something much more than that. It has to be so-called high resolution or high definition map in 3 dimensions. And to this, you need to add positioning, navigation, and timing, or P&T, if you will. That really would enable localization of the vehicles and mutual location of the vehicles among themselves. Now, at the moment, there is really not that much we are doing on the high resolution map except of providing them to the vehicles when we test them. But of course, the goal in the future is that the vehicles themselves would also create those high definition maps. So the previous speaker showed you image processing on one type of systems, but of course there's multiple vision systems that are used on the vehicle, and all together combined they can create a high definition map. So crowdsourcing would be something we want to look into as a future. I don't want to spend a lot of time on this slide. It's very busy, but the point is, which we actually have had today, the development of automated vehicles first starts from technology, right? We have the technology now. The question is, what is the level of autonomy that we have achieved so far? But the point, or the message to take home, is really without appropriate validation steps for the safety critical automated functions, automated vehicles will not be accepted by the society, and this was really the message from the first talk in the morning. But notice, technology can be ready, fully operational status, starting from the early design. At the same time, you have to watch how you want to make this your system automated or autonomous. So you can develop single technology, but then you start integrate it, creating a system of system, and at the same time, look into what you need to do for autonomy. So back to smart city for a moment is smart mobility. I just want to give you an example what technology is available right now to assure that we can navigate those vehicles or locate them. So let's look at the smart city and smart mobility component. And it's a little bit busy slide, but let me walk you through it. Do I have a pointer? The bottom? OK. So if you look at the smart city mobility, driverless vehicles, and the navigation component, you can think of two-pronged approach, local and global. So for local, really, is the proximity to other vehicles. You need to assure that there will be no collision. There is understanding of an anticipation of driving on other vehicle side, and your and your own vehicle, which essentially defines defensive driving, and you want to also minimize the energy in terms of, like I said earlier, minimum footprint and really less traffic. For this, really, imaging sensors are the best, and we already have had a little bit about the image-based navigation. High-definition maps may be helpful, but they are really not crucial. But again, you need to put your vehicle in the global system because everybody else will use reference system, which is global for path planning, route optimization, energy minimization, and so on and so forth. For this, global positioning system or global navigation satellite system with other sensors are required. But again, I'll explain in a moment, and you probably all know very well that this does not work everywhere. So we need to have a backup, and this is, again, the high-definition map is really absolutely crucial. So the high-performance computing and data storage really comes over here when the intelligent database is created, because this would be a depository when one can go and get this information. Now, for the clarity, there are two types of definitions I would like you to distinguish. Localization, which is lower accuracy requirements and about tens of meters, and it's really good for detection of the for car sharing or for the purpose of the insurance application or dynamic toll charging, but for navigation and steering of automated and autonomous vehicles, you have to have high accuracy. And it's not that easy to get in particularly in urban canyons when lots of us operate. So the requirement is of a few centimeters. It's really high. So single frequency GPS, which is on your phone, is not going to be sufficient. Even single frequency with differential correction is not sufficient. You have to have much more complex algorithms and, of course, communication system to provide information to each vehicle to get this accuracy. So there are a number of algorithms which we developed called, for example, real-time kinematic or precise point positioning. All of those methods require external information. So we have to have infrastructure, such as permanently tracking stations for global navigation satellite system, which will work in tandem with your receiver in the car and other receivers around you to provide a network which is actually located and moves dynamically with high accuracy. I still have to mention urban canyon will still in the effect. Even if you have this infrastructure, if you have masking and your satellite or the site of view is masked, you cannot see the satellites, your accuracy is going to drop. So we need to have multi-sensor systems which would allow navigation through those urban canyons, plus image-based navigation, which actually is very effective there. So as an additional support, I keep mentioning the map matching algorithms would be very reliable if the high-definition map is available. So map matching requires a priori map. Just very, very quickly, why GPS, which is so great technology, is not really effective to the point that we need to add multiple sensors. I'm not going to go through the error spectrum because we actually can deal with most of those errors which I marked in the figure. The problem is that we have those items in red is what really is making the solution, but GPS only, unreliable. There is a multipath, so in the environment when you have reflective objects, you have signal coming up, excuse me, via multiple paths, the accuracy drops. You also have a signal which is very, very weak. So GPS signal is very weak, and therefore is very easy to jam or spoof the system. Spoofing really is the consequence of the fact that the signal is not encrypted. So for example, Galileo, the new European system, has one of their services which provide encrypted signals. So this actually is very important for the cybersecurity of the vehicle or the network of vehicles. There's also another system provided by Iridium satellites, which is also encrypted. So the future probably would be GNSS combined with, for example, the Iridium system. Just to give you a sense what would happen if we use the regular localization quality receiver versus if we use the position algorithm, which I mentioned a moment ago. So there are systems already available and being tested quite extensively. One of them is the hexagon system. Excuse me, Terrasat X GNSS. Again, GNSS stands for Global Navigation Satellite System. This would be GPS, this would be European Galileo, this would be Russian GLONASS, Chinese Beidou, and additional space-based augmentation system. One of them is an Indian system, and there is an upcoming system which covers Japanese island and Australia. So there will be, right now probably, we have well over 100 satellites, and there will be still more. So the way the system works, remember I mentioned infrastructure. You've got the whole global reference infrastructure to compute the orbits of your GNSS satellites and possibly clock errors of the GNSS satellites. There's nothing perfect. You've got to know how much error you have. The local networks, which are, again, local infrastructure in the country, when you operate your system, is actually helping you to determine other error sources in the global positioning system observations, and you compensate for those errors. So the information is passed to processing center, and there is a way to send it to the user who is over here. User also receives signal directly from GNSS. So notice the external infrastructure is helping you to improve the accuracy of your vehicle. This particular system using so-called precise point positioning system. And if you notice, 4,500 stations worldwide belong to Hexagon, but there is many more of those. The governments, the universities, and the local organizations distribute those networks, and they are available to the users. So just to let you know, the system has been already tested here in Michigan and also in Germany, and accuracy, 95% of the time, was better than 1 meter, so it's actually very promising. Those are the areas in the United States when the system is going to be deployed for operational purpose in 2019. There is already one system which operates in the United States. Swift Navigation has launched Skylark system, which essentially is also based on the infrastructure of the corrections to the GNSS system. And there is also so Voyage is the company which deploys self-driving vehicles using Skylark. And somebody mentioned in the morning that you would like to see your aging parents or us when we are aging in those autonomous vehicles. Actually, this system happens to operate usually in the retirement communities. Those are gated communities when people would like to be independent in terms of transportation, and actually successful deployment a number of locations here is proving that the system works quite well. All right, just a few words about high-definition maps. I mean, comparing to what you see on the map when you navigate of your phone, comparing to the level of details and the quality of geolocation of that map, you can obviously see the significant difference. We need those maps for level 2 and higher for autonomous navigation. Of course, the challenge with those maps, because you can imagine they take a lot of space because of the number of details, but also the dynamic environment it has to be accommodated. There is a very quickly changing environment, so those maps have to be very frequently updated. It's just a very quick view of the Ohio State system we have built for collecting data to create the maps and also to simulate then use of this information for autonomous navigation based on image-based. So we have multiple Velodyne system, multiple cameras. This is just really a combination of the LiDAR system data. You can see a level of details that you can collect in this particular map. Now, of course, despite the fact that we have a number of cities right now mapped with high-definition maps or covered with high-definition maps, there are still many open questions. So this is a very expensive process. It's going to take us a long time to get those maps for every city. That's why I mentioned earlier the goal is at the moment to try to see if the crowdsourced data from the vehicles on the roads can actually be provided to update those maps as we go. They have to be, of course, verified. We mentioned many times trust, and we mentioned many times the accuracy and the safety. So those maps, if they are going to be used for navigation, they have to be very high accuracy and the public has to trust in this product. The public has to trust also in the navigation component with this GNSS combined with other sensors. Yes?
Do you find that data coherence is a huge challenge here? Because if you are crowdsourcing and you are getting apples and
Right.
oranges, how are you remediating that and getting coherence?
Right, so we are really kind of in infancy of this research. I'm going to show you example of collaborative navigation, how this affects the accuracy. But you are perfectly right. You've got to have information of the number of sensors and types of sensors and other parameters of the sensors that you are using. So we are just testing at the moment, but it's a little bit longer way to go. It's a good point. And of course, I have to emphasize, we are working with real sensors. So no matter what the goal is going to be, 99.9999% of the integrity level or assurance that there will be no failure, there will always be something. So it's just a matter of not really making sure that we can minimize that risk. And to minimize this risk with those kind of systems, you've got to have multiple sensors. You have to have redundancy, you have to have complementarity, and full understanding of the error spectrum. But the problem which comes with it, of course, is that every type of sensors can fail differently. So if you now try to test the system, you test it as a system of systems, but in fact, you have to test every single component and understand exactly what is the problem with the system, which component failed. So it's much complicated system to test as opposed to the regular vehicle. So I emphasize here that in order to meet this trust and the accuracy, we have to essentially adjust the standard and performance requirements for global navigation satellite system hardware and software because they have to now meet those stringent requirements of autonomy. And we also have to have very stringent requirements due to signal attenuation, interference, and spoofing. That's a big problem. Right? If somebody can, and we had a number of demonstrations how easy is to spoof GPS, with a $1,000 laptop and a smart student, you can actually send a false signal to GPS, and GPS receiver is actually following what you tell them to do. So it's very, very easy to do this. That's why a number of layers of cybersecurity are required. So again, to add to the value of GNSS, we have to, of course, add all those additional sensors. Inertial measurement units, LiDARs, radars, cameras, acoustic sensors, and any ambient signals of opportunity. We have worked with Wi-Fi, we have worked with cellular network and digital TV to augment the system. Now, of course, the question becomes now cost, complexity, reliability, right? So you can add as many as you want. But then you make the system more complex, maybe not always more costly, but always more complex. And then it adds additional problem to getting them tested reliably. This is just an example I mentioned a second ago. Two users are navigating separately, and they don't know of each other, but every frame, we call them keyframe. So every nth frame is sent to the main processor. And once the two frames sent by two or multiple users are isolated and found that they really come from the same area, the map is generated jointly by all those users. And we found the accuracy increase about 50% if you do that. And again, it doesn't take a lot of time and space because we don't send all of the images. But this is just an example of the two different sensors collected with different speed. If you see, I think one was even upside down, and then we're still able to get those keyframes together and start generating one map which navigates. Yes?
So if you have a bad driver, somebody that's driving down the wrong side of the street, do you have a mechanism that takes the third sigma away from the norm and opposite?
We are really not there yet. We really are demonstrating technology and the standards and finding what it is. It's a different story. Not there yet, but hope to be there at a certain point. So again, I don't think I really need to spend a lot of time on it. Those are the figures you could see from multiple providers of autonomy or automated vehicles. what you can, the thing which strikes me always, you see how much redundancy you have, right? The sensors are forward-looking, but some of them have long-range, mid-range, and short-range. The field of view is also different, so you are really fully covered, so the vehicle can see in multiple ways, so to speak. This is just an example of the, if I can run it, to show you the types of sensors we have on our vehicle, and eventually all those images or streams of images are really integrated to create a high-definition map, which we can then geo-register very accurately to have it to test now the autonomy, and let's say see how effective those systems are in terms of providing assured navigation for autonomous vehicles. I borrowed this slide from Curtis Hay from GM. He recently presented a GPS World workshop, and I think it very nicely creates the sense of the major component with the manufacturers now have to understand and combine together to assure that multiple sensors which provide navigation or localization to your vehicle can actually operate together. So notice that every sensor really has its own so-called body frame, so it operates in its own frame. Your vehicle operates in the global frame because you need to know where others are, and you need to know, or they know where you are, so you need to have one global frame, which in the United States is NAD83, could be WGS84, which is the Global Navigation Satellite System, a reference system, or could be international system, which is also used quite widely. Anyway, the point is you have to now find transformation and boresight among all of those sensors so we can combine the streams of information together. And one thing I want to point out, again, without going into all the details, you can, of course, expect there are pros and cons of the sensors that you are using, but the goal here is that eventually your sensors, in the combination that we have, would see what you expect the system to see. And notice we also emphasize here the separation between local frames and the global frames in which you eventually navigate. So those components of trying to make sure that reliability and availability is not compromised by the cost of the sensor oftentimes is really achieved by redundancy, as I said. You can have more kind of crappy signal, and if you have good processing of that signal, good ways of squeezing out information, you still can get high accuracy information even from the low-cost sensors. So I think I mentioned this already, the implementation challenges related to those multiple sensors and multiple reference frames that you are operating in. We need to have high accuracy localization has to be achieved in the predefined reference systems. So again, the cost of the HD maps, which have to be in the system, is one problem. High accuracy GNSS may be problematic in urban canyons when you really need to have other sensors. And now I'm going to touch briefly, time permitting, on the testing methodology. Normally, we have testing ranges all across the country. We have one at Ohio State Transportation Research Center, the largest proven grounds in the US to test vehicles. At the moment, what you can do to start testing is the simulation. So model in the loop, software in the loop, hardware in the loop. Eventually, you start testing. As you know now, we are testing also outside the testing tracks in the real world. And again, a couple of examples were given this morning. Now, what is still before us is the full development of the safety standards for new motor vehicles. There is a number of attempts, and there is a number of documents, among them ISO 26262 for road vehicles, first release of 2011. The current one, I'm not sure if it's been released already or is coming in 2018. To some extent, it's going to actually provide structured, as I say here, structured and generic approach to the complete safety life cycle of an automated electric and electronic systems, including design, development, production, service, processing, and decommissioning. So entire life cycle would have to be described in there. It's also defined in terms of the integrity levels, but I'm running out of time, so I want to just very quickly mention number one, and I think it was spelled out one way or another this morning, computer-based systems should be considered unsafe unless convincingly proven otherwise. You cannot just simply say, I debugged my software, it's good to go, right? You have to have a way to verify, and you have to prove that the system is working. Now, I mentioned that the updated release in 2018 will still not fully address the issue of autonomy, so we will really not have exactly the prescribed processes to do this. So it still remains a challenge. So the most of the time in engineering design and in automotive design, we use so-called V process or V model, which provides good foundation to derive those safety standards and do the verification. And that's really a pictorial description of what the V method is. So essentially, the right-hand side is able, or the right side of the V is able to test by verification and validation what the left side was. So you can see the design and architecture requirement and concept can be now verified through testing and verification, system validation, and eventually operation and maintenance. So the scrutiny here is based on the assumption that the left side is fully understood and known so that the right side can be used to verify it. And as you can imagine, it really does not work very well in autonomous vehicles for a simple reason. It's really a different environment. A lot of functionality there is done by artificial intelligence. And then you have test data when you test your system, which may not necessarily be reproduced to the same accuracy and the same standards as when you test your system. So this really, and it's not only this, there's also complexity of those systems, and there is also the fact that there is no driver in the loop makes it complicated. So like I said, this is still a challenge, and I need to run through, so I skip this. This is just an example of how vehicles are tested when you just test the vehicle driving in terms of repeatability of your truck. So let me skip this. So at the moment, vehicle level testing is insufficient to ensure safety. We've got to go to those systems and subsystems to understand what it is. So one way which is proposed, instead of one V, have multiple Vs, one for safety critical, and another one for operational aspects. So those are the things people try. It's just an example of our recent work, simulation-based testing of our deep learning neural network for image-based navigation. Again, complex system. I guess the previous speaker addressed this quite extensively. So those are the alternative methods right now under consideration for autonomy testing, and a couple of other examples here. Separate set of requirements allocated strictly to safety, and another one to operational functional requirements. So like I said earlier, 2 Vs to work with. Of course, there is still a lot of their left liability problem, and again, so on and so forth. Phase deployment, monitor actuator architecture is just one good system and fault injection alternative ways to test the autonomy. I just want to mention Ohio State has Transportation Research Center. We just broke ground for the new 540-acre smart center, which would actually be testing multiple autonomous vehicles. You would be having capability to create autonomous traffic there to essentially do the work. We also are part of so-called Smart Belt Coalition. So you can see Michigan, Ohio, and Pennsylvania. We are working together testing connected vehicles and eventually autonomy. It's just, I'm running out of time, I'm very sorry. I just wanted to show you the time progression of how the vehicles really developed when we, first in 1980s, we got the anti-lock braking system, and how additional technology helped us to be where we are right now. Prediction is around 2025. We should be able to have autonomous vehicles in the system. I just want to mention issue of private car ownership. Mobility as a service is currently what we take into account. And I think it's fair to say that if we have autonomous vehicles in the roads, it's actually be very transformative, because it's going to create different types of economy and also different approach to life. So if you think about it, all those are the areas separate areas of technology by themselves, which eventually are consequential to AV acceptance. And apology for running out of time. Thank you.
Do we have questions? Yes.
So interesting that people are developing the new GNSS. The challenge being urban canyons, for example, seems like the natural synergy would be 5G. And
Right.
I was wondering what
Right.
is the theory of 5G in the world of autonomous driving, automated driving, because it seems to be a great tool, but maybe it
Right.
doesn't work.
Well, yeah, actually, we don't directly work at the moment with 5G, but there are other groups which introduce this to, this is just another signal. This is an RF signal which you can use for positioning. You're absolutely right. TV signals were used as well. Any signal of opportunity, as long as you can time it properly.
What about in-vehicle sensors such as accelerometers? I mean, you know, years ago it'd be, inertial guidance systems, but obviously
Right.
those are well gone.
No, I mean, you can use still, the simple wheel counter, but normally you have multiple inertial measurement units, IMUs, gyros and accelerometers in those vehicles, and you use them in tight integration with the GNSS signal. They actually mutually work very well because IMUs would drift, GNSS is either solid or is not there, so they actually complement each other and correlate errors.
Thank you.
Other questions? No? Okay, well, thank you very much, Dorota.